Okay, so welcome everyone to today's first session of the conference. I think we can start now, and we are happy to have Lorenzo Rossi that will tell us about the global extraction of unpolarized transverse momentum distributions. Thank you very much.
Okay. First of all, I want to thank the organizer to give me the opportunity to talk here, and I want to talk regarding the last work of the MAP collaboration, that is an extraction of the unpolarized transverse momentum dependent distributions from a global fit. But I want to start talk also of the work in progress, what we are doing from MAP22. So, first of all, as I said, we want to extract information regarding the TMDs from the data, but we want to know the process from which we can start information. And the first process is the Drellian one, so a proton-proton or a nucleon-nucleon scatterings. Why we want to extract information from the Drellian? Because the structure function of the Drellian can be written by using the TMD PDFs in the TMD region. And if we go in that region in which the square of the invariant mass is bigger than the energy scale square, can be written in this way, in which there is the product between two TMD PDF, because we want to extract a quark from a proton and the anti-quark from the other proton. And this is the first process that we use in our extraction, and the other one is and this is the so-called W term, and the other process is the CDs one, in which we have the semi-inclusive deep and elastic scatterings, and the unpolarized structure function of the CDs can be written in this way, in which we have the W term plus the Y term. But if we look inside the W term, you can see there is the product of one TMD PDF and one TMD fragmentation functions. And I want to make two points. The first one is the fact that the W term dominates in the TMD region, so in the region in which the transverse component of the photon momentum exchange is smaller than the energy. And from the other point of view, the Y term dominates in the region in which QT is bigger than Q. And for this reason, we are working in the TMD region. We neglect the contributions of the Y term. Okay. For the non-expert, I put also the structure of a TMDs, and I explain the different parts of it. First of all, we have the matching coefficient that are perturbative calculable functions, and they are already calculated at many different orders that match up the collinear PDFs, because if we want to fit a TMD PDF or a TMD fragmentation function, we have to fix the collinear part. After that, we have two evolution kernel, because the TMDs has two types of divergences, means that we have two different types of evolutions. That is the Sudakov one and the Collins superkernel one. And the last two terms are the non-perturbative part of the Collins superkernel and the non-perturbative part of our TMDs. And the last two parts are the ones which we fit in our extraction. Here I put the table of all the available global fits. With global fits, I mean a fit of all the available data set of all the available processes. So Drellian plus zeta production plus CDs. And I want to talk regarding the MAP TMD22, that is the latest extraction, and it is also with SV19 with the highest accuracy for a global fit. So how we made MAP22? We use the Namaga-Parbat framework, that is a tools aimed to extract information for the non-perturbative part of the TMDs. And on this GitHub page, you can find all of the results, and you can try again to obtain our same results. Okay, MAP-TMD22. MAP-TMD22, we fitted CDs and Drellian, and we fitted an amount of 2,031 data points. And we made it at a high accuracy, as explained before, so N3 LL minus. To fit the CDs data, we introduced a normalization prefactor for the CDs beyond the next to leading logarithmic accuracy, and I explain how and why I introduced it in 2 minutes. And to parameterize the non-perturbative part, we use 21 parameters, and we obtain a very good agreement, a very good description of data. We can obtain a chi-square per number of data points equal to 1.06. So I want to comment step by step all of these points of the bullet list. And let's start with the data sets. As I said before, we fit the Drellian, so we fit the fixed target data, but also the collider one. But as I explained before, we have to stay in the TMD region, so where Qt is smaller than Q, so we have to apply a cut. And after the cut, we have 484 data points. In a similar way, we can do the same things for CDs, so for the Hermes and Compass data. And for CDs, after the cut remains 1,547 data points. I put here also the kinematic coverage of the dataset included. This is the high energy data, so the collider one. The red and the green bubble are the CDs, and after that we have here the fixed target. Okay, how we parameterize the non-perturbative part of our TMDs? For the TMD PDF, we choose a combination of a Gaussian plus a weighted Gaussian plus another Gaussian. And we put also an X dependency, and this is a standard form. I think that the first extraction in which they use this parameterization was PV17, but this is a standard form also for the collinear extraction, for example, an MPDF or CTEC or so on. For the TMD fragmentation function, we made a similar things in which we put a Gaussian plus a weighted Gaussian, and also here we put a Z dependence, in which we have introduced also another parameters that is a delta, because we want to put a shift in that part, and we parameterize also the Collins superkernel, and we parameterize the Collins superkernel in this way, in which the G2 is the 3 parameters which we want to fit. So in total, we have 11 parameters for the TMPDF, 9 for the TMD fragmentation function, and 1 for the Collins superkernel, 21 in. Okay, why introduce a normalization prefactor for the CDs? Let's make a step back and look to the Drellian. This is a plot for the PV19 extraction. And if we increase the logarithmic accuracy, we are going near and near to data, so our description improves if we increase the orders. But if we make a similar things for a bin of Hermes, we can see that the yellow point, the yellow band that are at NLL, describes quite well the data, but if we increase the accuracy, the description worsens in general. But this is for Hermes. We can make a similar things for Compass, but maybe it's better to look the ratio between the data and the prediction, and we can see that the ratio amounts to almost a constant factor. So why there is the problem and how we resolve this problem? Let's look to the observables, which we fit, that is the CDs multiplicities, and this is the ratio between the CDs TMD cross-section divided by the inclusive DIS1. But there is another important observables, that is the CDs collinear cross-section, that is the observables which the collinear fit groups use to extract information regarding the collinear fragmentation functions. And here I put a plot of an extraction made by the map FF in the 2021. And here, there are no problem of normalizations. So in the CDs cross-section, CDs collinear cross-section, we don't have problem of normalization, but in the CDs TMD one, yes. Why there is? Because if I integrate the CDs TMD cross-section over the momentum, we have to obtain again the CDs collinear cross-section. This is a simple mathematical equality. But in our case, this is not wrong. This is wrong. In fact, the normalization prefactor which we put is the ratio between the CDs collinear cross-section divided by the integral of the CDs TMDs. And we put this normalization prefactor before the experimental multiplicities. I want to stress the fact that this factor is independent by the fitting parameters, and it is also pre-calculated in our extraction. And by using this normalization prefactor, we obtain a very good description of CDs. In fact, here I put some plots of Hermes and Compass, and maybe it's quite difficult to see, but the description is very well. In fact, if we look to the value of the chi-square, we have a 0.87 chi-square per number of data points for CDs. And this means that we have a very good agreement between our prediction and the data. But let's look also to the Drellian. I put here some plots of fixed target and Tepatron data. And if we look to the chi-square, we can see that for the fixed target, we have a chi-square per number of data points equal to 1.24. And this means this is a quite good description, a good description of the collinear data, of the fixed target data. But if we look to the collinear ones, we have a chi-square of 2.06, and this is a fairly good description of this data. But this is affected by the Atlas data, because if we consider only the Atlas data, we describe them with a chi-square of 5.05. This is not good, but this is due to the fact that the Atlas data are the data with the smallest uncertainties in all our fit. If I remember right, they are order of 1 per mile. And this means that for a certain point of view, is very good to have small uncertainties because well-constrained the TMD PDF in that region, but for the other point of view, it's very difficult to go precisely on the data with our predictions. For example, these data sets that is described quite good, I think, if I remember right, is a chi-square of 6 or 7 per number of data points. Okay, let's look at our TMD PDF. Here I put a plot of our TMDs in X and KT. Here there is also only the replica 0, but maybe it's better to make some section of it in the 3D to go to a 2D plots. And this is what we obtain. And we can see that the confidence levels of our extraction is very small. And this means that we are well constrained of them. Maybe at low hex, we have quite large bands, but this is due to the fact that we don't have really data sensitive in that region, so maybe we need new data sensitive at low X to constrain them. I put also here the TMD fragmentation functions, and also them are very constrained. Maybe there is a quite strange behavior in the medium range of PhD, but this is due to presence. We don't know. I don't know that this is wrong or right. We say that this is. We need new the double lepton annihilation data to well constrain it. Okay, this is what we did in map22. What's the next steps? The first steps is to extract information regarding the Pion TMD PDFs, and we made it in our extraction map22 Pion, in which we fitted the Pion industrial data, so a negative Pion beam on a tungsten nucleus, and we fitted all the available datasets that are unfortunately only 2, and that are a small number of data points in general with a quite good description. If we look to 1.55, maybe is too high with respect to the Proton 1, but if we compare it with the other extraction of the pions, is a good agreement. And how we parameterize the non-perturbative part of the pion with a simple Gaussian with the same X dependency for the proton, and this is the results we obtain, and we can see that here we have large uncertainties, but it is due to small numbers of data points with a high uncertainties, experimental uncertainties. And this is the first step. The second step is to introduce the Monte Carlo sets. Why I'm saying introduce the Monte Carlo sets? Because in map22, we use MMHT 2014 and DSS. Both of them are Asian sets. Now we are working with the NNPDF and the MapFF extraction for the PDF and fragmentation function, because both of them are Monte Carlos. We are making a fit, and we have some preliminary results, and this is the comparisons between the map22, that is the purple bands, and with the NNPDF and MapFF, that is the red one, and we can see that we have a good agreement between the two extraction, but for the Monte Carlos, we have large uncertainties, and this is good for me, but also for us, because we have a better idea by using the Monte Carlo sets of the uncertainties regarding the TMDs. So another important thing of using NNPDF and MapFF is the fact that we are increasing also the perturbative order of the extraction, because NDSS was made at NLO and MapFF is made to N2LO. I made a similar things for a similar plot for the TMD fragmentation function. Okay, why important to go to N2LO for the MapFF? Because we can make a full N3LL extraction. What I obtained for the fragmentation function, I obtained these preliminary results. And it's quite strange because the TMD PDFs are compatible between the two extractions, but now we have different behaviors. And the question is why? But let's look also to the preliminary results we obtained for the chi-square, and this is what we obtained for an NPDF and MapFF. And if we look to the chi-square, the total chi-square per number of data points is 1.39. That is not good if you compare it with map22 that is 1.06. But if we look to the different experiments, we can see that we have an Hermes description with 2.72. This means that we are not describing well Hermes. And this is quite strange because in map22 we extract Hermes, for example, with 0.8, if I remember right. So why? I started to study this worst description, making a trip. So I started with map22, that is a good description of data, and I changed in only the PDF set. So we use NNPDF plus DSS, and we'll be obtaining a chi-square of 1.07. And this is a very good agreement with map22. So by changing the PDFs, we don't have many problems. But after that, I complete the path, and we made a fit with MMHT and MapFF, and we obtain a chi-square of 1.39. And we have an agreement in the first lines, but if we look, we have also a similar worsening from the bottom to top. So the worsening on the chi-square is related to the changing from DSS to MapFF. We are talking with the editor of the MapFF extraction, and I make a simple comment of it, but because I'm not a collinear fitter, they say that they know these behaviors, but it's related to the fact that by increasing the perturbative accuracy in their extraction, they discover new behaviors of the fragmentation functions, but also in the region in which we have data, the fragmentation functions have smaller uncertainties in general with respect to the DSS. So now the question is not why, but how can we solve this problem? We made this simplest things, if we think about it. We release the non-perturbative part of the fragmentation functions. So we take because up to now, the non-perturbative part of the fragmentation function in Kaon has to be taken equal to the non-perturbative part of the fragmentation function in Pion. Now we release it, so we take the same functional form for Pion and Kaon, but with different parameters. That is as simple as things, because the collinear fragmentation functions are made in this way. And what we obtain with this hadron-dependent approach, we obtain a quite good agreement, a better agreement with respect to the hadron blind. In fact, we have a chi-square of 1.11, and this means that we have a good agreement of it. But if we look, we have a good agreement for Hermes, for Compass, and this means also for CDs. Another important thing is the fact that the Drellian chi-square don't change. And this is a quite important thing, because if I change the fragmentation function, I really don't know why we have to change the Drellian extraction. And this is also an important thing to see, because I put also the plot for the TMD PDFs, and we can see that the green band that are obtained with this hadron-dependent approach are compatible with map22, that is the purple band, but are compatible also with the hadron-blind approach. This means the orange-red band. And this is fine, for the same reason as explained before. But if we look to the fragmentation function, we see some different behaviors for Pion and Kaons if we release the non-perturbative part. The answer is yes. Here I put the TMD fragmentation function of an up quark in a Pion and in a Kaon, and I rescale the Kaon TMD fragmentation function by a factor 4 because I want to put the same normalization to see the different behaviors. And it's easy to see that they have different behaviors, the Pions and Kaons. Okay, if I have time, 1 minute, 2 minutes, okay. I may want to talk regarding the last work in progress, that is, we started to study the polarized TMD PDFs. In particular, we start to study the helicity distributions. The helicity distribution describes a longitudinal polarized quark in a longitudinal polarized proton, and how we can extract information from the helicity distribution by studying this observable, the virtual photon asymmetry, because we have a direct access to the G1 function, but we can fix all of the other functions by using map22, for example. And here I put preliminary results of our extraction for a bean of Hermes, and we can see that we have a quite good description of these beans. but I put also some preliminary results for the bands of our TMD PDF, longitudinal TMD PDF for different value of X. Long story short, MAP22 is the latest global fit extraction for the unpolarized TMDs, and we have a good description of the data. MapPion22 is the first extraction made by the MAC collaboration for the Pion TMDs, and this is what we made. What we are working on are an update fit by using the Monte Carlo sets, by using an agent-dependent approach, and we are studying also the illicit TMD distributions. And I'm finished, thanks.
Thank you very much for this talk. Questions?
Very nice talk. So for Pion case, do you fit the collinear pattern distribution at the same time or use other parameterization?
For the collinear part?
Yeah.
We
for
use...
Pion.
For?
For Pion TMD.
For the Pion TMDs, we use X-Fitter extraction for the Pion PDF, and we use a standard form for the non-perturbative part, Gaussian and nothing else.
So you actually didn't do the simultaneous fit for the collinear PDF and the TMD?
No,
okay.
Not up to now.
Okay. So another question, I remember that there's also a significant part of the data for the so-called 5-star distribution at Collider. Are you guys using that or not?
Up to now, we are not using it, but I'm not expert, so.
Thank you. First, comments. I see you do not include the recent CMS measurements of the Torellian for the proton PDF, proton TMDs. So we have a new measurement at 13 TeV,
okay,
which is extended in the mass range from 40 GeV in mass to 1 TeV.
Okay.
Yes, and which is the most precise. I know you don't like that too much.
Yeah, but it's fine to have more precise data.
But so, yeah, this is really, I think, to be used. And we also provide the full uncertainties in terms of covariance matrices. So for each uncertainty, we look at the correlations bin to bin from each systematic separately. So there will be a talk tomorrow giving a bit more details on that, on how to treat that. But this is something we provide. We make a huge effort to provide to the community. It's not easy to be used, but I think this is a way to go.
We don't know this new release of data, but it's fine, and we implemented it in our extractions.
Then another comment. Once we go below above the Z peak for CMS for LHC data,
yes,
there are sometimes different definitions of the cross section in terms of do we include the gamma contributions or not, and this is the difference between Atlas and CMS. So just to point out that there might be a little tension if you treat that this way. And then my question is, what do you do in terms of theory uncertainties in this? I didn't see the details. What do you include?
With theory uncertainties means that uncertainty regarding the collinear PDFs or for example, other type of uncertainties, that is the kinematic power correction, mass corrections, and so on. Because we are considering now the full uncertainties regarding the collinear PDFs, because in MAP22 we evaluated the uncertainty by using an Asian set, but if now by using a Monte Carlo set, we are changing the replicas of the collinear PDFs one by one when we change also the replicas of our TMDs. That is similar to what we are doing in R23.
Yeah, I have actually a similar question regarding that. So if you when you showed your different points for when you start going up in resummation order.
Yes, give me a second.
Yeah,
a
this
lot of
global fit.
This one?
Yes.
Okay.
So it's not only that the points get farther away from the data point, which is it's that there, at least from the eye, it doesn't look like the series is converging, right? So you don't see smaller.
I don't give a right answer to this question, but this is an open field to understand because many groups saw these problems of cities. Alexei calculated the kinematic power correction, and also he said that there is a factor near 80%, 100. I don't remember what you write in your paper, but it's a starting point to understand.
Actually, concerning this stuff, say if you go to Pion TMD, so from your table, it's clear that actually you have a lot of problems with description of normalization of Pion.
Yes, we have a very high contribution for the penalty.
Provocative question. So shouldn't you use then the same trick in Drell-Yan, like you use in CDs? Because see, for example, here your second column tells that, let's say, for E615 you have huge problem with normalization.
Yeah.
Extreme. So
we know we can try.
I mean, to be consistent, if you do it in CDs, you should do it in Drell, and also for LHC, for all of them. I mean.
Sure. Thanks.
Hi. So you flashed this G1 XKT. Is it any different from F1 in KT dependence?
I cannot answer because we obtained that results in the last 2 weeks, but it's a work of our master students. So we have to...
You can just divide one by another and...
Yeah, we can make a comparisons very fast.
Other question was about your this bump in the fragmentation function. Is it in any way coming from the compass second Gauss or is unrelated? Or you just cut out this compass second Gauss?
For compass?
I mean, compass has the tails in.
No, we are neglecting the data. We are cut off.
But did you try to put this, Alessandro kind of was claiming that even if you cut that data out, when you put it on top of your curves, you get something.
What we observe is that if we fit the data in the TMD region, and after that we make predictions, our predictions goes very well also for the data outside the TMD region. But we are not, we didn't try to fit that.
That was what I wanted to see. If you put this multiplicity on top of the compass data at large PT, how it will look like.
Yeah, we can do it.
Matthias had a question.
I'd like to come back to the theory errors. On page 8, you showed some parametrizations of the exponents of the Gaussians and also the 3 Gaussians added up.
Yes, just a second. Here.
Now, a priori, this looks very arbitrary, and the question is, besides varying all of these parameters, do you try to estimate an uncertainty for this assumption of the fitting function?
Yes, kind of, but it's a quite preliminary things for the TMDs. For PDF, for the collinear PDF, are already use some tests to understand the parameterization. Now it's quite difficult to understand for the TMDs, but we are starting on it because we are releasing more and more degrees, so we have to understand that if we are doing the things very well in general.
Because later in the talk you had plots, several actually, where kind of things were oscillating in the tails, and it's probably a consequence of adding too many Gaussians. And the errors were very small, but the oscillation seemed completely artificial, so somehow this needs
we put this parameterization because there is some studies for the Parton model, because, for example, we need a weighted Gaussian to describe the couple quark, the diquark couple for the proton, the diquark couple in the proton, or, for example, a Gaussian to describe a free quark on it. These are studies in the Parton model made by Pacchetta, Cottogno, and so on in 10 years ago, if I remember right. But yes, we have to study if our parameterization is good, if we are overfitting, and so on.
Thank you very much again. We'll move to the next talk now. No. So next we have Valentin Moss that will tell us about the extraction of unpolarized TMD PDFs from global feed to Drell-Yan data at M4LL. Thank you very much.
Thank you. Okay, so I have the fortune to have already had a very nice introduction to TMD PDFs and the extraction thereof. So what I'm going to present to you is our extraction from this art collaboration consisting of Ignacio Shimemi, Alexei Vladimirov, Pietro Rita, who are all here, and myself. And yeah, we extracted the unpolarized quark TMD PDF from Drell-Yan data. So that's a difference between this talk you just heard. We only use Drell-Yan data, not CITES data. And we did this to the accuracy of N4LL. So let me start with my outline. So in the beginning, I would like to give you an overview of like a theory that I consider to be necessary to understand what we're doing. Then I will talk about the data that we include and the collinear PDF that we choose. And then I'm going to show you our results in some discussion. So for the theory part, let me start by describing what the TMD distribution is. So the TMD distribution, this is what this is in this first line. Is this for matrix element of this TMD operator, this blue part here, of which you can see a sketch down here. So it consists of two quark fields which are separated along the collinear distance parameterized by Zn, so collinear light cone direction. And then on top of that collinear separation, they also have some transverse separation denoted by this transverse distance b, which is the Fourier transform of the transverse momentum. And these quark fields are also gauge connected, but this gauging is not direct, but it goes from one quark field along the light cone up to infinity, whether it's plus or minus infinity along the light cone depends on the process. And at infinity, it takes into account this transverse distance and then reconnects to the other quark field. And due to this transverse distance, these quark fields, these gauge links, do not lie on top of each other, and therefore they don't cancel, but have to be taken into account completely, which is one of the features of TMDs, which makes them a bit, in this regard, more complicated than collinear PDFs. What I didn't mention so far is this gamma structure that we, gamma structure, which is represents one of these three gammas. I mean, in general, it can be any Dirac structure, but these are the ones that contribute to the cross section the most. And if you insert one of these gamma structures, then you get this separation, or you can categorize the distributions you get first with this gamma structure, which corresponds to a polarization of the quark. And then once you did this, you can parameterize these three terms once more, and then you get this this diagram that people typically show when they talk about TMDs, where you have the TMD distributions categorized by the polarization of the quark and the polarization of the nucleon it originates from. And in this talk, in this extraction, we only focus on this function, F1, this unpolarized distribution, unpolarized quark in an unpolarized nucleus, because this is the one that is most accessible from experimental data at this point. Okay, I basically will skip this this slide because we've already seen in the previous talk what the Drell-Yan process is. So I will just skip this and talk about our model. So also this formula you kind of already seen in the first talk. So this unpolarized distribution is this formula here. So we have this convolution with the coefficient function and the collinear PDF. I'm going to talk about this later. And then the transverse momentum or the transverse distance information is encoded in this function f and p, the non-perturbative part. And our model for this non-perturbative part is like this. So it's 1 over cosine hyperbolicus of lambda 1 times 1 minus x plus lambda 2 times x, and this times b. So essentially, one parameter should more or less describe or grasp the behavior of the TMD PDF at small x here, and at one at large x. And this function has to fulfill a few conditions. One is that if b turns to 0, this function should turn to 1, which it does, right? So if b goes to 0, then this cosine hyperbolicus goes to 1. And on top of that, it must be integrable, and therefore we have one constraint on these parameters. They both have to share the same sign, so both need to be positive. Otherwise, you would find some critical value of x where this argument here vanishes, and then the function is not integrable anymore. So what I didn't mention so far is this f. So our extraction and our model is flavor dependent, so we distinguish between various flavors. The flavors we distinguish between is U and U bar, D, D bar, and all the rest. This means all the other flavors share the same parameters. And that means that we have 2 parameters per flavor. So at this point, our model consists of 10 parameters that we need to fit. So what I didn't mention so far is that the TMD PDFs are not only functions of x and b, but also of 2 energy scales, mu and zeta. And on this slide, I just show you how this evolution within this double energy plane looks like. So basically this evolution factor, which is this blue term here, where you have this path integral, or this basically curve in this 2 energy plane. And I just want to be brief about this and only mention that it also depends on this function d, the Collins-Sopper kernel. And this Collins-Sopper kernel can be expressed like this, where you have this d at small b, and then this integral over gamma cusp plus d and p. So these green expressions here, they are perturbative series in alpha strong and logarithms of the scale and b. So they can be written in perturbative series, and in this table here, I basically state at which accuracy this extraction is done. So at which term each of these perturbative series has been cut. Right? So for example, gamma cusp we take into account up to alpha s to the power 5, and the hard coefficient function for the cross section. The cross section is at 4 loops in alpha strong. So, but why I talked about this is because this Collins-Sopper kernel has a non-perturbative part. Also, we've also heard this in the talk before, and we have this ansatz for this non-perturbative part of the Collins-Sopper kernel. So it's 1 coefficient times b star. Where b star is essentially proportional to b at small b, and at moderate b it saturates and becomes constant. And with this term plus this additional term here, proportional to this logarithm. So this adds another 3 parameters to our model, so 3 parameters for this Collins-Sopper kernel, and with these 10 parameters we already had from this transverse distance-dependent ansatz, we have 13 parameters in total for our fit. Okay. Now I'd like to discuss the data and the collinear PDF that we used. I'll be rather brief about this, but essentially here you can see a phase space diagram in X and Q of the data sets that we have included in our fit. What I'd like to mention is that we have a large range of this resolution scale from 4 GeV up to 1 TeV, which is very nice because it gives you it just tests the evolution with along this plane very well if you have a broad range. Also, what is new compared to previous extractions, to my understanding, is that we have the W production at ReLIAN included. So these data sets here, these purple sets. And in total we come up over here. We have 627 data points if we include these sets after cuts. Compared to other extractions, this is quite a good number. I will essentially be very short here. So the data sets that I just showed you before, on them we have to impose some cuts. And well, the most important thing is that this ratio, the Qt over Q, must be small because that's the limit where TMD factorization is established. However, of course, you need to make it some finite size such that you have some data points that you can fit, and okay, this is the cut that we come up with. And now I would like to spend some time discussing this slide. On this slide, you should get an idea of the importance of the choice that you make for your collinear PDF. So in this study, they extracted the TMD PDF with one model for different choices of the collinear PDF. And you see on the left side how the TMD PDF then looks like as a function here of x. Basically what you should see is that they are very different if you choose different PDF sets. And they are compared to an early extraction SV19. Right? And also, not only that do the distributions change, but also the parameters that you would extract strongly depend on the PDF set that you take as initial condition. So this choice is kind of it's very, very important, and it's also gives you some uncertainty on top of your extraction that is kind of difficult to control, because it's like a discrete choice that you make between the different PDF sets that are available. And in our work, we choose this MSHT 20 PDF set because it prevailed as the strongest candidate in this study here. Okay. Now, for the rest of the talk, I will present to you our results and also some studies that we made on them, like some checks. So the next plots will all kind of look very similar. So you have like two plots. So on the top, you have the differential cross-section versus the QT, the virtual or the lepton pairs transverse momentum. You have the data points, and the blue curve and band is the theory prediction. This data is so precise that you don't even see the experimental errors, you just see this bar. So therefore there's also this lower plot here, which is this plot normalized to the theory prediction. And here you can see the data points with errors, and also this blue band, which is our theory uncertainty. You should also, especially for this data set, you should look at these numbers here. So this is like this gray curve here, this or band is a 5 per mil, or okay, from here to here 10 per mil band. So this data is very, very precise from Atlas, and you should see that we can describe this very, very precise data quite well. And overall, for all data points combined, we get a chi-square per number of data points of 0.96, which is very, very nice result. Okay, now in the next slides, I will show you the similar plots, trying to cover the whole phase space that we used in our fit. So this is at 13 TeV, center of mass energy data from CMS at various spins of rapidity, which is at a high resolution scale and also moderate X. And essentially also here you see we can describe the data. Some feature that I didn't mention earlier is these dots. So these data points, if they are filled, if their data points are black, it means that they pass the cuts that we impose on the data point, so they are included in the fit. And the empty circles represent data points that are not included in the fit. And also the more you move to the right, the larger QT gets, the more you leave the TMD factorization region. But we should see that also these white data points can be described for the most part. So this is some data set from LHCb at also 13 TeV mass, center of mass energy in rapidity bins, and this is at small x or smaller x in our phase space region. And then I have the data sets at very low resolution scale, the fixed target experiment. So this is what I talked earlier about. Sorry, yeah? This is the lowest resolution scale that we have in our fit, is 4 GV, up to 5 GV bin. And this is all, everything here is also with uncertainty bands, but it's probably very difficult to see because the uncertainties are that small. Okay, but in general, also here we can describe the data quite well. And this is some data set. This is from Atlas at 7 TeV. This is just to convince you that we can also more or less describe the data that are that we don't include in the fit. So even though these dots here are black, it means that they would pass the cuts, or they passed the cuts, but this whole data set is just not included in our fit. Okay. All right. Okay. And now, I mean, what I showed you earlier is that we can actually describe the data. I mean, this is nice, but I mean, why we do this fit is because we want to extract the PDF, so we want to know the TMD PDF, so we want to know how the TMD PDF looks like. And here you see the TMD PDF as a function of X and B for the flavors, for U flavor on the left and for U bar flavor on the right. Yeah, so this is kind of, at least for my personal understanding, like the main result. This is why we do this. And yeah, what I mentioned this earlier, so if you project this to the plane B equals 0, then you more or less reobtain the collinear PDF. Okay. Now, we did some comparisons, some checks of our result. One of them was that we did, again, the same extraction with the same model, etc., same methodology, and only change the PDF set that we use. So, I mean, I already mentioned this. We use this MSHT20 PDF set. So this is our extraction. It's a green band, and it's normalized to the green central value. And it's compared to the extraction that you would get if you use the PDF set, collinear PDF set, NNPDF 3.1. What we also checked is the impact of the uncertainty of the PDF. So we, because we were able to process the uncertainty that comes along with the collinear PDF, and we checked in this plot basically the impact of not including this uncertainty, so only using the central replica for the PDF set. And for the ones, this plot is giving you an idea of then how the data description looks like. So what you see is, or what you probably would expect is that the central value does not change at all or only slightly. I would say, okay, this more or less confirms this, and the uncertainty band shrinks a lot, and also this is what you see. Okay, so it looks a bit orange, but it should be red. So the red band is the extraction without taking into account the PDF, collinear PDF uncertainty. And for the same problem, I just show you the TMD distributions. So here the green band is our extraction, and the black band is our extraction without PDF uncertainty. So also here you see that more or less, or only slightly, does the TMD PDF central value change, and the uncertainty shrinks a lot. We also, 5 minutes, okay, thank you. We also use this W boson data, and we are also able to describe it quite well in terms of the chi-squared, but what you see here is that these experimental uncertainties are quite large, and yeah, so therefore the impact of this data set on our extraction is more or less negligible. Here I did I'll show you some plot where we have one selected parameter, the parameter at large X, at big X, for our extraction, the main extraction, and then the same extraction without this data set, and you see that neither does the central value change nor the uncertainty. Essentially, we changes just a bit, but barely visible. And then, which is very nice here for this, okay, it says PDF uncertainty, it should say no PDF uncertainty. Central value stays the same and the uncertainty shrinks. Basically what you've seen on the previous slides already. Okay, now I talked about the TMD PDFs standalone, but we also fitted this Colin Sopper kernel. As a reminder, it looks more or less like this. I mean, it looks like this. I just omitted the sums over. So sum over n and k are implicit here. And yeah, what I would like to mention is that it's a good agreement, especially with the extraction of the map 22 fit. Yeah, and this is how it looks like. And we also just recently checked the impact of this additional term here. And without this term, the fit got significantly worse, so it's very justified to include this additional term here. Okay, and then we also did this scale variation check where we have variate our scales mu star, and mu OPE at different orders of accuracy or increasing orders of accuracy, and you see that here there's deviation. Or this basically this is the uncertainty. This reduces with increasing accuracy. And okay, and here you basically see the same normalized to the to the final order that we use in our fit. Okay, with that I already come to my conclusion. So what we have done in this work is a first of a kind and 4LO extraction of TMD PDFs for a flavor-dependent model. Various checks have been done, so everything is more or less behaves as expected, and we have a very nice quality of our fit with a good chi-square result of 0.96. And for the nearer future, we're actually just currently working on a CDIS fit. So we like in the talk before, you've heard that the map collaboration fitted CDIS and Drell-Yan, I think at the same time, if I understood this correctly. And we now fitted the Drell-Yan data, and using this result, we will fit the transverse momentum dependent fragmentation function using CDIS data from Compass and Hermes. Also, what you've heard in the talk earlier, we can use this result to fit the Pion TMD PDF. And once this earlier point here is done, once we have this CDIS fragmentation function, then we can use these results for impact studies for the ESC. So we can make predictions once we have these CDIS results, or the fragmentation function results available. Okay. With that, I conclude, and I thank you for your attention.
Thank you for your talk. Questions for Valentin? You can start on this side now.
Yeah, thank you for your talk. I wondered whether you could make a bit more precise what you mean that you have a preference for a certain set of collinear PDFs.
No, okay. I showed you this one slide where basically I talked about this this study about the impact of the collinear PDF choice on your TMD PDF extraction if you have a flavor-dependent model. Well, and I mean, the point is, one point is that in this study, this MSHT20 PDF just gave the best result.
Best chi-squared is what you mean then, or?
I think so. And,
okay.
We also did essentially, I showed you that we did this extraction using an NPDF 3.1, and I think there also the chi-squared is a bit worse. It's not as good. So that's one point. But I mean, at some point we have to make a choice. For this is the current state of the art. But one problem that comes along with this is also what I mentioned, that we have some uncertainty that comes along with this that we cannot estimate. Kind of. I mean, this uncertainty band that I showed. This grasps the uncertainty of the experimental data points and the uncertainty that comes along with the collinear PDF set. But I would say it's more or less the statistical error only, but it does not give you a grasp the systematic error that you make by choosing one of the PDF sets. But I'm not sure if I answered your question.
Well, I was just curious what your choice is based on. Was it based on the chi-squared, basically? That you tried different ones and this one looked the best, and then you're like, okay, we have to choose one, so... I'm just...
Well, so, I mean...
May I comment here?
Yeah.
So, of course, we didn't make a choice just on chi-square, but more like on smoothness of replicas, because if in PDF we have many replicas which oscillate very extremely, and if you try to put them in your code, the code became unstable. So that's why when you fit, it's not very convenient. That was, for me, that was main technical motivation to choose it, but generally we can choose any of them. And we did actually fit with different. It was just more convenient to use them as HT.
Okay, thank you.
Can you go to your B dependencies of U bar? You had the plot.
This two-dimensional function.
Yeah.
Yeah.
No, one-dimensional actually. Then probably is next. Yes, I was trying to understand what will be the ratio as a function of B, of your U and U bar. Actually, I'm more interested in KT dependence of the ratio. Mm-hmm. Because there are like predictions that seqworks should be kind of wider. So if you go to large KT, at some point you may have more of seqworks than U quarks, for example. Is this something that you can see from here?
You can see
from previous plot. From previous? How you see that?
Plot.
In this place should be vice versa. So something what is right.
Is it exactly vice versa, or?
It's more or less exactly vice versa.
Okay.
So and here indeed you see that for U quark you have this kind of longer tail to the right. So between in KT space it will be much sharper.
Here, this one, right?
So you already see here that when you go to large KT, your U bar may be more than U?
Yep.
Fantastic.
Okay, I can show you the same plots in KT space.
That will be very nice.
Some more questions?
Thanks for the nice talk. I have a lot of questions, but I'm interested on two of them now. First of all, it's interesting that you fitting also the W boson exchange, Andrelian, but how can you understand what is the right transfer momentum exchange? It's measured, but there is the release with the bin in the momentum of the boson. Okay, nice. Just to know. And the other things is the plot you put for Atlas 13 TV on slide just a
13 TV.
Yes.
Mm-hmm. This one?
Yes.
Uh-huh.
I don't understand it because you have a chi-square per number of data point equal to 3.7, that is for the replica 0, or this is the mean of the chi-square. And after that, there is a plus 16, so I don't understand. This means that your collinear PDFs explode in that region, or you are not well constrained that data?
No, okay, so to my best knowledge, I think the central chi-square that we show is the chi-square. I think it's not the average of a chi-square. We also use this replica method, but it's the chi-square you get by using the average parameter. Okay.
Okay.
And then why then you ask why this tail is so large, basically why this uncertainty is so big.
Yes.
Okay, I would assume that it goes along with this high precision of the data, that you have some replicas that just go wrong. Okay, let's not say wrong, but they just produce a bad chi-square, and for this precise data, you get a lot of these data sets, replica sets that produce a large chi-square, therefore this is what you get. But, so I assume it's mostly correlated with the precision of this data set.
Yeah, it's
because, I mean, you see, I mean, this is, yeah, for this it looks like this, here it looks like much more reasonable for the total data.
Yes, I know.
I would say it like this. So you see this band, right? Blue band. Yeah. So, but it's just a kind of shaded area. Some replicas inside of that band goes, with a bit more oscillation than others. And of course, for this precise data they generate, band is like that.
Yeah,
but
we know, but I
crazy.
expected that by introducing the flavor dependence, maybe you can well constrain the TMDs, but it's my idea. Yeah, maybe it's wrong. And I have another question, but I don't know if I have time.
Short one, please, because there's another one.
Okay, if you go to the plot for Atlas 7 TV that you not fitted.
Yes. Wrong direction. This one, right?
Okay, maybe I don't understand, but you are saying that you are describing well that data.
Okay, I mean, I think I said
reasonably well. If you look to the upper plot, light, but if you look to the ratio, not too much.
No, I mean, for this first data set, this first rapidity bin, I would say it's kind of okay. Here, I would say it's bad, and here I would say it's reasonable.
Okay.
But I mean, you're right. I mean, this is, I mean, in the like preliminary tests of this extraction, we also had this included, and then at some point we exclude this data set because it more or less never got a very good result. And I think also in your extraction you have problems exactly with
yes,
this
we have
set.
problem, but
so,
we put on the fit and we see what happened.
Yeah.
I want to understand why you are neglecting the contribution of them.
No, I mean, I think the argument to neglect this is because we see that it doesn't work, so it doesn't work well. But so we rather exclude data sets that would drag.
But you made some compatibility tests to exclude them.
No, if you, I mean, if you have some data set that doesn't work well, you could also just argue, okay, here it doesn't work. Why would you want your fit to be dragged into a direction to data set it cannot describe? Maybe there's something wrong.
Yeah, maybe we can talk
this is, to my understanding, the argument. I mean,
yeah,
it's
maybe
also fair
data, you have to include them.
Yeah, maybe you can discuss this over a coffee better. So
I mean, it was just the same question. I mean, okay. if you don't describe data and the solution is not excluding data from the fit, I mean, it's not the right choice in my opinion.
You're absolutely right. I agree with that.
I know, but there are points. I mean.
So I mean, okay. We could do some study including this data set and see what the high field is. I mean, I don't disagree with you, but I would say it's a choice. And I would say if you have some data that really gives you problems, then at some point it's fair to exclude them. But if you say all data sets like are correct, then of course you should.
Oh yes, sure, because also has start to study if these data are compatible or not with the others. So it's a open field to understand the Atlas 70 TV's data to include in our fit or not, but we can discuss later.
Yeah, okay. Let's keep this discussion for the coffee break. Thank you very much again to both speakers. And we reconvene at 11-ish.
Wait. Wait. No me grabes, espera. No me grabes.
Good, so we start the last part of the morning session with Carlo Flore that will tell us about towards global reweighting of TMD densities. Thank you very much.
This works, yes. Okay. First of all, I would like to thank the organizers for giving me the opportunity to present our latest results that we are developing now, together in collaboration with the Torino group, where I am now, and Cagliari group, and Alexei Prokudin at Penn State Berks. So we have heard about unpolarized TMDs in the last session. Now we move towards polarized TMDs. We've heard about TMD factorizable processes. I will talk about non-factorizable processes, but I will present a suitable model to try in any case to get information about the TMDs we want to study and see what can happen when we look at these kind of processes. So let me start by something not new for most of the audience, that usually we look at the single transverse spin asymmetries, usually in semi-inclusive processes, to get information about the three-dimensional structure of the nucleons. We access them through TMD factorizable processes like CDIS, Treliani, ±into 2 Edwards. But we know that, especially when we look at the polarized case, so when we want to have information about polarized distribution, data sets are very limited. They are ratios of structure functions. There are not as many data for polarized TMDs as for the unpolarized ones. And so we need to find a way to get more information about TMDs in some regions that are not covered by the data. So when we look in general at polarized phenomena in inclusive processes, these processes allow us for probing TMD effects in complementary region compared to semi-inclusive kinematical region compared to semi-inclusive processes. And in any case, with a careful approach in what we want to study or not, we can also think about studying universality and factorization breaking effects, because it is true that we know that these kind of inclusive processes, they do not factorize in terms of TMDs, but so far no one told anyone how big are these factorization breaking effects. If the effects are over the 1%, then maybe one can just do suitable analysis and take into account also this as an uncertainty. And in general, from the phenomenological point of view, we have plenty of data measured at RIC, for instance. The last ones are with very tiny uncertainties that covers an interesting kinematical region for the TMDs, especially when we go to large X. I will talk about 2 polarized TMDs. The first one is the Sievers function that you see here in the Torino-Cagliari notation or in the Amsterdam notation. That is a genuine TMD distribution. There's no collinear counterpart at leading twist. And it's expressing the correlation between the proton transverse momentum, proton transverse polarization and intrinsic transverse momentum of the parton. We extract it from the semi-inclusive DIS in this azimuthal modulation of the CDIS cross-section with the ratio of structure function, and we are sensitive to the quark Sievers function. I'm sorry. And we know that the Sieverts function is not completely universal, but has a modified universality because it changes sign due to the initial and final different structure in terms of color flow and initial final state interactions between CDs and Drellian. The other polarized function I will talk about is the Collins function. It's a genuine TMD fragmentation function. And in this case, we describes the correlation between the transverse polarization of a quark that is fragmenting into an observed hadron in the finite state that is emerging with a transverse momentum. We extract the Collins function. We heard also yesterday the talk by Xishuan about the Collins function from global fits of semi-inclusive DIS, where we cannot where we can discriminate about the sign of the Collins functions, but also from the azimuthal asymmetries through the usual double ratio methodology in E plus E minus into two hadrons, where the two hadrons are almost back to back with a small imbalance. As I will talk about inclusive processes, we need to have a suitable formalism to describe them. The formalism I will adopt is the so-called generalized Parton model, with an extension of the Parton model in which we take into account all the intrinsic transverse momentum effects explicitly in the kinematics and in the distributions. When we write the cross-section for an inclusive polarized process in the generalized Parton model, we start with a suitable ansatz in which we write a factorized formulation of the cross-section in terms of TMDs. I'm not claiming here that we are using TMD factorization. I'm just saying that this is a suitable approach to an operative starting point in terms of the same quantities we want to study. In the generalized Parton model, we cannot directly describe the sign change of the Sieverts function. So later, a Corrugage invariant formulation of this model was developed by Leonard Gamberg and Zhongbo Kang, including initial and final state interaction through a one-gluon exchange approximation, and recovering in this way the sign change of the Sieverts function. So the observable I will look at is the so-called single spin asymmetry in polarized proton-proton inclusive production of hadrons in polarized proton-proton scattering. The asymmetry is nothing but the ratio of polarized the difference divided by the sum of the cross-section when we reverse the transverse polarization of the proton in the initial state, and in this model is proportional to two contributions. One is the Sieverts contribution, and one is the Collins contribution. In the GPM and in the CGI GPM, the Collins contribution is always the same. There's no process dependence. Collins function is universal, and so we will not. When I will present results, there will be the same Collins contribution. But in the case of the Sieverts, we have to take into account these two differences in these two models. So I will present results both in the Corrugage invariant generalized Parton model, the CGI, and in the GPM. The difference is that in the CGI, we can do one thing. We keep using the same Sieverts functions that we fit from semi-inclusive DIS data, and instead of changing the sign of the Sieverts function, we compute new partonic cross-sections that have modified color factors. So essentially, these guys here in the CGI have a different color structure. For instance, if you look at a partonic channel with two different quarks that are colliding, you include initial and final state interaction, and you'll have these guys, color factors, that are modifying the partonic cross-sections without the color factors included. In principle, there is also a contribution from the gluon-Sieverts effect, but in the kinematical regions that we will consider should be, it was already verified in the past, should be negligible, and in what follows I will neglect the gluon-Sieverts effect. Now, I would like to remind you first about what's the reweighting method and what we are doing now. Reweighting is a very well-known technique, especially in the context of collinear PDFs. Fits, but through the reweighting, what we can do is that we can assess the impact of some data on the extractions that we already have without reperforming a global fit. So very fast procedure, very interesting just to have at least a hint on what could be the impact of new data that is measured on the PDFs that we know. It has been used both in the Bayesian framework, is the framework in which I will work, but also in the Asian approach. And we have already applied the Bayesian reweighting in this paper 2 years ago, reweighting the quark-Sieverts functions through inclusive jet production at RIC. In general, when we look at Bayesian reweighting, the starting point is that you consider your model of TMD that depends on some sets of parameters that have a prior probability distribution. For each of when you take a set of data, you can define a chi-square in the usual way. Hopefully, in the future, we will get the covariance matrices. But for the moment, usually this is the situation that we're at, because we have only uncorrelated uncertainties. And when you want to represent the uncertainty on the fit parameters, usually you can do a Monte Carlo and you generate some parameter sets, and for each set you can compute a chi-square in the same way. Then what you can do, you apply the Bayes theorem. So starting from your prior on your parameters, you can compute the posteriors given the new data using a suitable form for the likelihood. When the likelihood is taken as the probability to find new data confined in a differential volume dy around y, so when you compute the likelihood on the data and not on the chi-square, as it's done in some groups that fits collinear PDF, you get these exponential weights. This was the original work made by Giel and Keller. Notice that here a factor that is proportional to the number of replicas is missing, because it's just renormalize everything to the number of replicas so that these weights are normalized to 1. So through these weights, you can compute for observables expectation values and variances in this way. In what follows, I will use modified weights compared to this one. I will rescale for the delta chi-square as it was shown here in this paper. That is also it's a rescaling that allows you to reproduce also the Asian reweighting. In our case, our fits can also be the uncertainty of our fits can also be studied in the Asian approach, so we can correctly reproduce the Asian uncertainty. And I will show asymmetric uncertainties. I will show as a central value the median, and all the bands that I will show will be at the sigma confidence level. Now, this is all the work just for one fit. So imagine this is what we have done for the Sieverts function in the past, but now we want to try to find a way to reweight simultaneously Sieverts and Collins extractions together using the same data set. So the point is that we want to extend this technique to global simultaneous reweighting. We have to do an assumption, although maybe for the information that we have at our disposal, we think it's a correct assumption, and we think that when we look at two functions that depend on different parameter sets, f and b, they are statistically independent. Now they will contribute to the same observable, like in the case that I will show later, and for each of them you have some number of parameter sets, n sets for f, m sets for b, for g, sorry. You take an observable that depends on both fits, and so in general, since they are statistically independent, you have to compute all the possible combination of the different parameter sets. So for each of the combination of the ith parameter set for f and the kth parameter set for g, you'll have an observable that will depend on two different indices. you have the observable, you have the data, you can compute the chi-square for each of them. You get some weights that will have now the dependence on both sets. You just generalize very easily the formula that I've showed you before. So you will have the sum not only on one of them, but also on two of them. In general, this can be an issue because this number of combination can be very, very large. In our case, especially, we usually run a Monte Carlo in the parameter space. We generate 100,000 of sets to have a complete reconstruction of the parameter space to have a faithful estimate of the uncertainty on our parameters. So you can imagine that order 10 to the 5 parameter sets for A, order 10 to the 5 parameter sets for B. We have order 10 to the 10 combination, and it's an endless job just to get the results for one observable. So we need to find a way to reduce this number of sets that we can use to get the same results also. We found a suitable compression algorithm in this paper by Daniel Pitoniak and his students, where they had a similar problem, and they were sampling. They were describing another asymmetry that depends on the combination of two on two fits. You have a certain number of replica for one. You have another number of replica for the other, and they started to sample the values of the asymmetries computed with a certain amount of replicas. And you see, statistically, you can compute what is called the Welsh t-statistics that is defined in this way. This random variable tells you that when the distribution of the sample value, sample combination and 1 and N2, you start to increase this number, and 1 and N2 are, and 1 is usually smaller than N2, you start increasing the number of samples that you get iteratively, and you see that at a certain point you arrive at convergence. The convergence is reached when the absolute value is such that the p-value of this variable is larger or of the order of 0.1, so you get statistically equivalent distribution. So you have a representative sample for your full sample, and you can proceed without any issue. The underlying assumption here, it's clear, you have Gaussian probability distributions. Since we show asymmetric uncertainty and we discretize everything, we employ the t-test to find an optimal size for the representative sample, but we sample directly the parameters and not the observables. We sample on the parameter space. We compare also the median and asymmetric uncertainties for the samples, and we want to reach an optimal size for the sample to get the same results. To show you how this compression algorithm works, we took the old results waiting for the Quark-Sieverts function. This is the data that we used. This is not the, besides the details on the data, this was the result that we have got for the reweighted curves. We've had 200,000 Monte Carlo sets. We sample only 1% of these sets, so only 2,000 sets, and we put on top of each other, and we reproduce the same results with just 1% of the entire sample. This is you can also see it clearly when we look at their weighted curves with 200,000 sets, or just in color for only 2,000 sets for up quark, Sieverts function on the top, down quark on the bottom, GPM on the left, CGI on the right. And if we look again to magnify even more this effect, when we look at the self-normalized curves, you can clearly see that we get exactly the same uncertainty for the reweighted functions with just 2,000 sets. So this is encouraging, and we want to do the same, but now sampling the Sieverts sets and Collins sets. So we want to simultaneously reweight the Quark-Sieverts function, transversity, and Collins functions. These two guys are extracted together in semi-inclusive DAS. We will use data on pi plus minus production and pi zero production measured at Brahms and Star that covers complementary kinematical range with respect to CDs. They have a value of XF that is between 0.2 and 0.6, That means that we are spanning in XBRKern for the functions all the values starting from the value of XF that you probe up to 1. So a region that you don't, in which you don't have any data from any semi-inclusive reaction. I will show preliminary results here based on this fit for the Quark-Sieverts function and this fit of the transversity and Collins function that we have done in 2021. We sample 2,000 sets for Sieverts, 2,000 sets for Collins. These Collins sets are sets that are respecting the software bound. The sets for the Collins and transversity are sets that are respecting the software bound for the transversity, but without enforcing it in the parameterization. This was the main point of our work. So this is the transversity that we use, in which we apply the software bound a posteriori, and compared to some other older extractions, we see that the valence transversity has a much larger uncertainty, and the central value is no longer very close to the bound, and out of the initial 100,000 sets in that paper, the 16% respect the software bound when we apply the constraints on the parameter a posteriori after the fit, and out of these 16K sets, we sample 2,000 sets using the compression algorithm. And we sample, and when we look at the predictions only for the Collins band, comparing the full sample of 16K sets and the sample sets, again, we get the same uncertainty band, and we are confident that we can go further and apply the reweighting with this sample size. And by the way, these large asymmetries in the past were not seen in this model at all. So even just the first application of this procedure for not applying, not enforcing directly a software bound in the parameterization allows you to have better compatibility with and larger asymmetries in inclusive processes. So these are all preliminary results that I will show you. I got it last week, and the work is not yet ready. On the top, you see predictions for and data for pi plus measured at Brahms. On the bottom for pi minus, again on the left CGI, GPM, and on the right CGI. These are the unweighted curves. We apply the reweighting procedure, and we get the reweighted curves. And it seems that preliminary results are promising in that sense, though we have some discrepancies in describing data. Same when we look at the production of pi zero, where we have the largest asymmetries that we measure at two different values of rapidity, of pseudo rapidity on the top and on the bottom. Again, left GPM, right CGI. Again, unweighted curves, we apply the reweighting, and we get our reweighted curves. So to conclude, this is for the moment what we have and what we are working on. We know that these processes are not TMD factorizable, but we hope that at least in this suitable model, we can get complementary information on our polarized TMDs in these processes. We developed an extension of this Bayesian reweighting with a simultaneous reweighting of two independent TMD extractions, and we developed also a compression algorithm that allows you to allows for faster computation and reproducing the results for the full sample. This data allows us to improve the knowledge on the TMDs at large X, so it's complementary to the CDS data and to the JET data. And for the first time, we have shown that the proper usage of positivity bounds, think about what I told about the software bound and the transversity, allows you to reduce the bias that you introduce in your fits. And if in future we want to arrive at a point in which we will be able to quantify the factorization breaking effects, that I think personally it's something very interesting per se, reducing all the bias that we introduce in our fits will help to have more faithful estimate of these factorization breaking effects. Of course, this is what I showed is just preliminary. We have to update these fits with new Hermes data that is out, and that's all on my side. So I thank you for your attention.
Thank you very much for your talk. Questions? Carlo? No questions? So I have a question on the positivity bounds.
Okay, sorry. Yeah, I have also backup slides if you want.
Okay.
Please, go.
Just something more philosophical. So,
Okay.
Can you really go that far with positivity bounds in the sense of?
So what I showed here for the TMDs, for the transversity, you have a positivity bound that is a so-called software bound that says that the transversity, the x-dependent part of so the collinear transversity is always less than the sum of the unpolarized and the helicity. Helicity for down quark is negative, so the bound for the d-transversity is much more tiny. And we showed in this paper that if we don't enforce directly the constraint that automatically allows you to fulfill the software bound throughout the fit, at the beginning of the fit, but you just do the fit with the parameters that are free, and then you apply the software bound a posteriori, you get a different result. But this result is more faithful because, let me show you the slide that I have in the backup. If you look at the green band, this is the fit in which you automatically enforce the bound. If you don't impose the bound, you have a larger uncertainty. So essentially, you are underestimating uncertainties if you directly impose the bound, and you don't get the correct information out of your fit. And this is even more magnified when you look at the self-normalized curves. This white area is the area in which you have data that you fit. You have order 30% of uncertainty for the transversity when you fit with the bound automatically enforced. If you put it a posteriori, you have a much larger uncertainty, and this is something that you should expect. Otherwise, you are biasing your extraction at the beginning of the fit.
Okay, thank you very much. And are there more? So usually there's when you're doing any kind of effective theory, there's a few positivity constraints. So can there be any more? I'm not sure.
Okay, the case of transversity is, let's say, is maybe a borderline case because it's something that also people doing collinear fits of the transversity observe. When we published the paper, at the same time there was the work by Aurore Courtois and her PhD student that worked on the diadron production. They've studied the same issue and they got the same conclusions as us in two different approaches, in the TMD one and in the collinear one. There's Pavia people that is working on it, and they're very, very well known. And in the case of other PDFs, there are two issues. If we believe on positivity bounds, think about, I don't know, we take the Sieverts. The Sieverts has a positivity bound, should be less than twice the unpolarized TMD, but we don't know nor the unpolarized TMD, nor the collinear fits at large X. So what's the meaning of the bound there? How can we control that? Same can happen for other functions, but these are the cases that I've studied myself.
Okay. Thank you very much. The next one. Okay. Okay. Vale. Gracias. Okay, good. So in our next talk, Harutya Navakian will tell us about the studies of 3D nucleon structure at Jefferson Lab in the present and the future. So thank you very much.
Okay. Oh, okay. So hopefully the findings that we have will help to extend that universe. So you see we have a bunch of limitations in, for example, theory is not able to handle the large transverse momenta at a lower Q square, and I'll just present measurements from JLab where you have QCD in its full glory. Is a strong interaction, so you will see a lot of very big effects, asymmetries, polarized measurements. You see, basically we are able, because of the huge statistics and multidimensional measurements, we can dissect what we call cities and try to understand parts of it and understand the, for example, contributions that are typically neglected. So what we have here are the electroproduction facilities. Is this? Okay. So you see going from a lower energy JLab to 12 GeV, then going to 22 compass and EIC, and our kinematics. So we detect, it's important to realize that we are not measuring any specific moments, but we measure the full cross section, and that is not always obvious. What are the implications of measuring this 5-dimensional or 6-dimensional if you have also the transverse spin, and how off somehow itself. Is it like battery? Use this one. So basically measuring these azimuthal modulations, we get access to underlying structure functions and hopefully to all kind of distribution non-perturbative objects like giving contribution to these structure functions. So want to point out, so that we know the variables in the game. There is this Z, which is a fraction of the energy carried by the hadron, a fraction of the virtual photon energy. So we have the transverse momentum of hadron or two hadrons, depending on the measurement. And we have all these series of azimuthal modulations. Now, basically also here the conference is more like focused on this FUUT. Those are the most popular structure functions. Unpolarized transverse photon contribution, and then you have Sievers, and then you have Collins. So I will try to make the case that this really to link what experiment measures to what theory is trying to analyze. There is quite some work to do and figure out what are the contributions that are not really additional contributions in the experiment that one has to take into account. One of the myths that exist in the CDS community is that if you go to higher energies, then a bunch of all these structure functions, they just disappear because they are higher twist. So as you will see, indeed some of them disappear, but not because that they are higher twist, but because they have kinematic factors that are suppressed. And what we can, you see this epsilon, for example, here plotted for different facilities, and you see that when you go to very large, high energies, epsilon goes closer to 1, and some of these contributions will be suppressed. Doesn't mean that they are small, actually. The structure functions are small. So it is very important to keep an eye on this kinematic factor when we look, and we will see that at compass energies, at least so far highest polarized experiments, all these higher twist functions, they are actually very significant, the ones that are not suppressed kinematically. And now, what you see with this crosses is that the most relevant observables, according to theory, they are actually most complicated ones in the sense of additional contributions that were never quantified. In fact, these are the longitudinal photon contributions. So one has to understand what exactly those are, how big they are. There is some intuition coming from DIS, but DIS will never tell you what will happen at high PT, for example. These functions can be small, but you go to high PT, they can be very significant. No one ever measured them, so there's no clue what exactly they are. So the point here is that really to understand the unpolarized cross-section or sieverts, you still have to sort out the longitudinal photon contributions. Another complication comes with the Collins measurement that also is, as you will see from slides and from different measurements, is also not trivial observable, because it is basically, the cross-section is written for an inclusive hadron, while we will see that things are a lot more complicated. So it requires some more understanding to have proper interpretation, to link it to actual dynamics, what is measured for the Collins asymmetry. So one thing I want to point out here is that this type of full cross-section written with all structure functions and then structure functions composed from the convolutions of distribution and fragmentation, we basically have, for CDs, we have also for DVCS, but in many cases we don't have, and we actually need this because, for example, if you want to do radiative corrections or what, to understand what is the impact of different contributions, so it is critical to have the full cross-section. Now, that is just part of the business. So here is the full proton in its full glory. So we in CDs we assume that we basically work with the current fragment. So we kick out a quark and then it produces some hadrons, and that's what the cross section was about. So basically giving you the probability for this hadron to have the given z, pt, phi, and so on and so on. Now, in reality, this is not the only thing, and even in the current fragmentation, there are when you measure experimentally observables, you have a bunch of contributions which is important to understand. Especially if you go to large Z, it's clear that you start to pick contributions from exclusive processes. So this is the limit of exclusive processes, so they are described by GPDs. Then we have this, what is called semi-exclusive production, which some people now are trying to understand, because this is background both for the semi-inclusive and for exclusive. Then we have TMDs, and then we have fracture functions, which are the hadrons describing hadrons in the target fragmentation. So experiment basically measures everything, and then you have to separate them. One important thing to notice here is that most of the asymmetries, as the ones at least I will show, they have in semi-inclusive, exclusive, and target fragmentation limit, they have the same origin. Basically, if your asymmetry is already coming from the struck quark, so that means that you deal with for example, polarized quarks. So this asymmetry, physics of it is the same, whether you produce semi-inclusive or exclusive, and you will see that in fact if asymmetry is sitting already in the distribution, in the quark itself, so semi-inclusive is basically just the dilution of this asymmetry producing more and more hadrons. So understanding of the exclusive limit of these observables is important. And we will see that, I mean, the cross-section that we wrote, the structure function part is generic for all of them. Of course, the content of the structure functions will be different depending on which processes we look at. So this is like big slide showing all JLab experiments for different targets, the proton, deuteron, helium-3, all 3 holes. Measuring is just to have some big picture. You see a bunch of experiments involved in measuring all kind of azimuthal modulations with access to TMDs. Now, the new ones now are related to measurement of the longitudinal photon, because from that picture of epsilon dependence that I was showing, you noticed probably that only at JLab you can actually measure the longitudinal part, because you have some variation of epsilons. So you have different beam energies. These are different beam energies. They have different, as a function of Q square and X, you have different epsilon values, so you can measure the cross-section and separate the longitudinal parts. This whole C experiment approved, and then there are 2 experiments from hole C and 1 experiment from hole B that will be running in a month or so. So we will have this UUL pinned down, at least in a range of X and Q square covered by JLab. So this approximation that was used even in the projections, that this ratio of UUL and UUT, which is this R, that is kind of PT independent, this was typically used in evaluation of possible effects. This is something to check, obviously. I mean, there are all indications that this, the R will be increasing with transverse momentum. Coming back to this favorite experimental slide that our theorists don't like much, is the full PT dependence of the multiplicities. And you see this comparison of compass and Hermes, and then the compass going to a large PT. And we were always claiming that if you really want to understand what is going on, to understand the dynamics of production of hadrons, you have to sort out the large PT, and I will make the case why it is important. So you see some difference between Hermes and compass, and we track down in these effects in JLab are bigger. That is important to understand the simple phase space effects, which means that in certain kinematics you just don't have enough energy to produce higher transverse momenta. So going to higher energies, it gives you higher transverse momenta. Unfortunately, Hermes didn't have enough luminosity to measure the higher transverse momenta, so these tails are not visible. And that this tail, the origin of this tail, I think is very important to understand. And there were a bunch of possible mechanisms discussed, and of course people try to link it to perturbative contributions. And here is my example of the phase space problems that you may have. You see, this is just JLab measurement of multiplicity as a function of PT, and this is the standard Gauss. You see that in certain kinematics, you just don't have enough PT even to make the Gauss, so you don't see the tail here. Once you correct for that, then you perfectly describe the standard fragmentation functions coming from much higher energies. So to some extent, these complications coming from JLab is more about the high statistics rather than about the non-applicability at lower energies. So this is our favorite framework, and that was discussed. I think during the discussion session we can come up with what we call validation. I understood that what different people put different meaning in the word validation. So now I'll try just to go through possibilities that within this framework, what can be changed to describe the higher transverse momenta. So what is the source? So I list here at least 7 possible reasons why you can have these tails that are clearly have nothing to do with the perturbative part. So attempts, of course, to play with the TMD fragmentation functions. But there are different predictions, and I will show some of them, that what can be different in transverse momentum distributions. For example, U quarks opposite to the proton spin can be much wider than along the proton spin. So this is something that can be, I mean, people use the unpolarized quark and they don't care that parts of these unpolarized quarks can have very different transverse momentum dependencies. The other thing is that D quarks may have a much wider transverse momentum distributions than U quarks. Those are, I'll show some pictures for that. Another prediction is that the C can be much wider. So, which means that C is relatively small contribution, but when you go to very large transverse momenta, C contributions can be very significant. So all those can generate additional Gausses that were used by Compass to fit the second Gauss. Outside of this machinery, there are, as I pointed out, the possible contributions from longitudinal photons. And this, especially when you go to large Z, where you have more contributions from exclusive states. And in exclusive limit, you have vice versa. You have longitudinal is a dominant contribution, and transverse is the higher twist. So understanding PT dependencies of UL will help, means that the UUT part of the cross-section actually can be much smaller if we properly subtract out of the data multiplicities the part coming from longitudinal photon. There is also effects coming from the vector mesons. This I'll show how those can affect the transverse momentum distributions. And also, of course, the radiative corrections that the procedure was not even properly developed for CDs up to now. So all those can change the way we look at CDs that was already available and tell us something how to proceed with future CDs measurements. Those are a few examples that I pointed out. You see predictions by Strickman, Weiss, and Schweitzer that when you go to large KT, C starts to dominate. When you go to large KT, this is the ratio of quarks along the proton spin to the opposite to the proton spin, so it changes significantly, and actually delta U can become negative at large transverse momenta. The ratio of U quark to D quark goes down, means D quarks are much wider. So those are all effects that can either can be picked by phenomenology from a lattice or can be some parameters to fit. So that's why I was asking what is the ratio of the C quark to valence quark, for example, as a function of KT. This is another plot. This shows the transverse momentum distributions. This is from Monte Carlo by Albi Gerbizzi. That, oh, okay, I have to go faster then. So this shows that the vector mesons are, you see, they are wide, and this will be the same thing with the direct pions, while the decay pions have much smaller width in transverse momentum. That can also generate you two different Gaussian distributions. So theory. Now, this is what theory is telling us. So there is a mess. You have target fragmentation. You see these blobs, they don't have fixed limits. And theorists, of course, try to go into what they call safe kinematics, go to very high Q square. We have to take into account that at very high Q square, you also have very small effects and you have very little statistics. While already clear from the all analysis that was done that you need multidimensional measurements if you want to sort out what exactly you are measuring. So that's important that while the light is here, the effects are here. So this is where like the guy is looking for his keys. Okay, so how we deal with this? So what we measure, what you see here is the beam spin asymmetry, and beam spin asymmetry, which we can measure with huge statistics. It tells you that where exactly is the struck quark. In fact, so you can separate the current fragmentation from target fragmentation. You see this on the example. For example, here you see, you go to exclusive limit, is obvious that you have to kick out U quark. And this is the polarized U quark, so asymmetry is positive. Now when Z is small, then your U quark is not anymore in the pi plus, but is in the neutron. Since the asymmetry is for pion, you get negative. To get a pure D quark contribution, this channel pi minus delta plus plus is where exactly you know that you kicked out a D quark. So polarized D quark, asymmetry negative. If you look from the proton side, this is a beam spin asymmetry from proton side, you see how the asymmetry is plotted as a function of x Feynman, so exactly following this scheme. You see the region in x Feynman where you for sure are in target fragmentation, a region in x Feynman where you are in a current fragmentation. So basically here proton has the kicked out quark, here it doesn't. So this asymmetry can be just used to separate different kinematic regions. Since I have little time, so this is the way we see basically the redefined. See this? If you have a proton detected, since you can detect all particles in the final state, so a proton, and then you look the missing mass, then you see all kind of exclusive states, then you go to continuum, where this is what we call CDs. The measurements of single spin asymmetries here, those are these two objects here describing longitudinally polarized quarks. I said that all these beam spin asymmetries, they are coming from longitudinally polarized quarks, because like you can exclude other contributions by the fact that your pi plus and pi zero are always the same, like Sieverts. These are type of Sieverts effects, so asymmetry coming just from the U quark. And this asymmetry, you see, everywhere I put this epsilon factor, so this is the one that will be vanishing at higher energies. This is a higher twist asymmetry that is not vanishing, and you see Compass measures all the same 4 or 5% asymmetries that we have for Sieverts. So all asymmetries are of the same order, and if they are not suppressed, then they are measurable at high energies. These asymmetries plotted versus Q square, for example, the cosine Kahn effect, which is not disappearing, you can see from epsilon factor, or the sine phi, they show actually increase with Q square. So they are not disappearing with Q square, which is something that definitely requires some more understanding. Now, in addition, the beam spin asymmetry can allow us to separate contributions. For example, what you see here, these beam spin asymmetries, you see for pi plus, for pi zero, as I said, positive is coming from U quark. For the pi minus, negative, coming from D quark, polarization negative. But you can, when you look at rows, you see that in some place of kinematics they are positive. So basically this kind of diagram. In a very small t, where you have more of the dominance of the gluon diagrams, then you get negative. Also, we observe also negative asymmetries for the phi, which has only this contribution. So looking at the behavior of the asymmetry, you can separate these contributions, and if it indeed comes from the polarization, so that this can be considered as an indication that delta G, at least in this kinematics, is negative. I'll go quickly through the point that I was making about the Collins effect. So if you measure two pions, you can make the invariant mass, and immediately you see that all two pion combinations, pi plus, pi minus, pi 0, pi plus, and so on, they are all dominated by vector mesons. And this is the plot from Gerbitzi showing what these vector mesons can do with your Collins asymmetry. For example, this is what you measure. These are pions. And these are actual pions. So basically, in the asymmetry, you have a dilution factor of 5. So if you measure this Collins effect just for pions without understanding the details of the dynamics, the interpretation will be very complicated. The same thing exists for kaons, and for kaons, this can explain why you have very different asymmetries for pions and kaons. And this I just put a slide for the EIC to show the multiplicities of the pions and actual multiplicity of the direct vector mesons and direct pions. You see, even in EIC, you have a tiny multiplicity for pions. So most of them are coming from decays. So one has to sort out this. Here you see another picture how these asymmetries of the rho 0 and rho plus, they are very significant, and how these rho 0 and rho plus asymmetries show up in the pion asymmetries. So it will be very hard to interpret any kind of asymmetries if you don't understand the source and the different contributions, which at least we understand the kinematics when you can access direct pions. So quickly through observables, the double spin asymmetry, again suppressed at higher energies. We can measure as a function of PT access to G1, and we have this data. I see the people are fitting Hermes with the huge error bars. You can measure the additional particle in the target fragment, which gives you completely different weight for the struck quarks that you can, fracture function mechanism should be used. This is a leading twist observable, again linked to the longitudinally polarized quarks in unpolarized protons. So I can come to this later on. The asymmetry measured, this is a sinusoidal asymmetry measured for, now here compared two different versions. You see, longitudinal target, longitudinal beam. We claim they are all related to longitudinally polarized quarks, and they are exactly the same. One has to understand why these two asymmetries are the same, structure functions the same. Another important thing to learn from here is that in the target fragmentation, you don't see any medium modifications. So it's just a target fragment. Okay, this is another leading twist asymmetry that can be, is not suppressed, so can be accessed in EIC. This is the list of things. So one thing I want to stress here is that once you properly you understand all the contributions, you have much better chances for the formalism to work for this data. And this is my summary, just stress that importance of multidimensional measurements, importance of separation of different contributions, the importance of validation. I hope we will discuss the validation of all kind of extractions, and you see that we basically introduce a completely different dynamics, new dynamics of how the hadronization is happening. Thank you.
Thank you very much for this talk. Are there questions? I have time for a couple of questions.
Can you go please back to the plot with double Gauss, whatever,
two-slope plot of compass. It was somewhere in slide, 6 probably, about two slopes and observed compass. Yes, I just want to mention that, first of all, here Q square is 1.2. So, and also, the second slope appears at this PT bigger than 1, so bigger than Q. I mean, you cannot talk about any factorization theorem and any perturbation theorem.
I'm sure in the support slides I have from compass much higher Q squares. The tails are always there, and I really put those pictures for the discussion. It is not just this is one particular plot with the tail, but you have these tails everywhere.
Okay, and they always start at 1, or they
have
moving.
This is like a relatively low X beam. That's why also Q square is low. But they're like Q square 9, and you have the tail.
Okay, so on discussion we will continue.
Yeah, we can continue.
Any more questions? No. Thank you again. We continue with the next. Sorry about that.
Yeah. Okay. Should work now? Yeah, guess so.
Okay, thank you. So for the last speaker of this section, we have Filippo Del Carro, who will tell us about Pion TMD's analysis at Compass and Amber.
Yeah, I will talk. This talk will be mostly a bridge between experimental results and what can you actually say through that using theory. So in the first part of the talk, I will talk about the Compass DY program and the possibilities, the capabilities that gives to the analysis of the 3D structure and the 2D structure of mesons mostly. Then I will show an impact study made on pseudo data for Pion TMDs using Compass kinematics and Compass errors, and made through the map framework. And then I will talk about the future possibilities for meson structure at Amber, which is the newborn child, if you want, of Compass. It's almost 1 year old now. So just to give you an idea of why we need more data from Drelian for the Pion, I want to show you the TMDs in nucleons, which in theory they should be a little bit more difficult to extract. They are hadrons. But in this case, we have more processes, more data, a lot more statistic, and the knowledge, the current knowledge of TMDs in nucleons is much better compared to Pion TMDs. Even if they are meson, even if they have a simpler structure, they should be easier to get. Their processes, the Drelian that we use to study them, they have much less statistic. We have a much limited amount of data. So what we are doing to correct this issue is taking new data, releasing new data for the Pion Drelian using taken at Compass in 2015 and 2018. And here I just wanted to show you briefly what are the characteristics of this experiment. First of all, we have a beam with a really high purity, 97% of pi minus, which give us a really clean process to actually analyze the 3D structure. This is at 190 JV and which a much higher intensity, which give us good statistics and so good statistical errors.
And as a key element, we have a polarized target together with the aluminum and the tungsten target. So we have a different variety of targets, which with a good absorption of hadrons and a good precision in the tracking of our process, thanks to 300 tracking planes. So what we get from this setup is a diverse variety of targets, which give us a flavor separation with a really high accuracy, given by tracking, purity, etc. And here, just to talk about the target, we have tungsten, as I was saying, aluminum, and NH3, as you can see in the picture there. We have two different peaks for aluminum because they were in different positions, also for NH3. But what I was saying is like one of the main features of one of the still open issues about TMDs is their flavor dependence. How do they depend on different quark? How can we do that? Trying different combination of proton and neutrons, which is different materials from the target, to actually get this separation, to get our measurement. And another interesting feature of TMDs is obviously TMD universality. We have the same exact TMD function for different process, Drell-Yan and CDs. So what Compass is trying to do is releasing a dataset which cover the same exact kinematic coverage for CDs on transverse polarized proton from 2007 and 2010, and another dataset which covers the same exact kinematics using pion-induced transverse polarized Drell-Yan from the 2015-2018. So we have covering the same Q-square range, we have a minimization of Q-square evolution effect between these two processes, and we have a unique condition with similar X and Q-square range to test TMD universality thanks to this new dataset. Just to give you an idea of the set of the range of the mu for the Compass kinematics, we have taken out the low mass region where we have a large background contamination. We have taken out the intermediate mass region where we have high dy cross section but also a low dy signal compared to background ratio. And we have obviously taken out the J-psi region, which will be useful, obviously, for other analysis, but it's not really our focus in this part of data set. Finally, we focus on the high mass Drell-Yan region between 4.3 and 8.5 GeV, and this is beyond the J and J-psi peak, and psi prime peak. We are in the quark region and in the quark region cross section, but we have a low Drell-Yan cross section. So in this case, we are. That's why I was saying we have less data. This is a really low cross section measurement, so you have to run it for longer time with many different targets to get a good description. And here, just to give you an idea of the dy analysis cuts that we did. So I was saying we are in the high mass Drell-Yan. We have a really good purity, and we are around a peak of xn of 0.17. And again, we don't have much cross-section, but still, thanks to running a lot, we finally arrived at a new release, which is the first new result for this kind of measurement that was presented for the first time at SPIN 2023, 1 month ago. And what I wanted to stress is this is really an improvement compared to the limited data set that was coming just from Fermi lab. And this is what we had for the first time in the last 30 years with a similar kinematic coverage as E615, but with better statistic and similar systematic. So we are compatible with the previous data set from Fermilab, but we have a good improvement on the diversity of targets with the tungsten, NH3, and aluminum, and a better statistical error. Going from this, I wanted to kind of test what are the capabilities of this new dataset, making an impact studies. what we is something that we have already seen in the talk from Lorenzo Rossi. And I just wanted to show this. This is the DY process that we use. So 2 hadrons, one of them, it's sorry, 1 hadron and a meson, a pion, going to 2 leptons, and we get the structure function F1 UU unpolarized, and this structure function can be described as a convolution of a F1P that is taken from map collaboration global extraction from 2022. And we use also the, not map22 pion, sorry, just map22. And we use the, this proton function to actually fix and try to find the pion TMDs polarized using the map framework. So map framework was presented before by Lorenzo still, and was based on data from E537, E615, with an accuracy of N3LL. The non-perturbative part and the evolution kernel are shown there, and you can see there are basically the usual choices for the non-perturbative part with the Gaussian weighted. And for the evolution kernel, we are using the Bmin, Bmax. So this is, as I was saying, a generation of a DY prediction. So a data set, not really, since we are still waiting for the actual data for Compass, I just wanted to do an impact study using their actual uncertainties. So actual statistical errors and actual systematic taken from the experimental analysis of the data, but using the map framework to generate prediction based on the actual Compass kinematics, on the actual Compass region of X and M and Qt, and using the map22 pion TMD extraction from map Nangapar, but from the last October in 22. We generate a set of pseudo-data, so no actual data, but same kinematic and same uncertainties, which are actually, we are kind of relieved to see that they are compatible with the E615 data, and with much better. So, going through the fit, the impact study that I did using these pseudo-data, you can see that we are using still the map framework. We did extraction of 200 replicas, which are really compatible with our CMP, which are Compass map pseudo-data. And same here, you can see with just the replica 0, so the one that is not Gaussian oscillated. You can see that we have a really good description of the data, but this is kind of expected since they are pseudo data. The part that is most interesting is that we have a good chi-square, even with the addition of these pseudo data to the original data sets. But we have a much smaller uncertainties on the definition of our pion TMD. So what I wanted to show with this impact study is that we have a hint of smaller uncertainties in pion TMD PDF with the inclusion of Compass result. So for the first time in, as I was saying, 30 years, we can have a better description of pion TMDs, a new data set to play with, if you want, which offers us also an interesting occasion to actually study flavor separation for this pion TMD PDF. With this, I want you also to look at the future of our meson spectroscopy program. So with the Compass, now it's a concluded experiment. We are still doing a lot of analysis on the previous data taking, but Compass is gone, and and now we have Amber. So the future of meson structure is the Amber physics program, is in the former Compass experimental. We have availability of both hadron and muon beams. By the way, we also have a positive and a negative beam available in a wide range of energies. And on one side, we have reused the large dipole magnets and the most recent compound detector, but we have also improved the particle identification and tracking through implementation of new detectors and an update of the existing one. With this, I want to show you the planned physics program. So we just concluded the phase 1, which is the one who was first approved by CERN, with the proton radius measurement and the p-bar production cross-section that just ended last month. And now we are starting phase 2, the preparation for phase 2, which will be concluded beyond 2029. And as you can see, there is a really interesting section of this planned physics program that is for measuring structure. So we will have a dy measurement, Drellian measurement with pions and kaons, using a beam of charge kaons and pions, with a different target of carbon and tungsten. At the same time, we also will have prompt photon measurements using still pion kaon on this time liquid hydrogen and nickel, and finally kaon-induced spectroscopy. So just to give you an idea, it will be a kind of varied. Now I was saying it will be a really large variety of target and a variety also of beams with the counts and pions with different charge, positive, negative. So this will be a kind of a new playground to actually test for flavor separation, for different effects coming from counts, pions, looking at spectroscopy and looking at the 3D structure. So it will be a set that will cover a lot of open issues right now. Finally, just to show you the Ember improvements that will be on the current knowledge of pion structure. Right now, the current limits for our pion structure is that we have mostly heavy targets, so we have a lot of nuclear effects. Some of the measurement that we did in the past for pions were actually not even published. And most of these previous work, were not measured with both beam charges, so there is no C-valence separation. What we plan to improve on this, we will have a high energy intensity pion beams with really high intensity both for pi minus and pi plus, using compass-like apparatus, so it will be also, we will able to compare with the previous dataset, and we will have a segmented carbon target. All of these will give you pi plus and pi minus beam on C and W target, which will improve PDF flavor separation. On top of that, using these different charges from the beam, we also aim at the first precise direct measurement of the pion C contribution. So to conclude, this talk wanted to give you an idea of the capabilities of Compass and Amber for the analysis, for the investigation of the 3D structure, that is TMD-PDF, and I hope I convinced you that Compass is a unique framework to study TMD-PDF universality and evolution, thanks to its features. Pion TMD extraction, in particular, are now based on a limited number of data, but Compass' new dataset could help to better understand them. And finally, looking at the future, Ember planned physics program will give us new tools to look at meson structure to pions and counts processes, giving us a new look, a new eyes to look at the flavor separation and the C-valence contributions. Thank you.
Thank you very much for your talk. Some questions?
Thank you for interesting talk. And to start with, I would like to complain a bit.
Yeah, please do so.
5 or 6 years ago, I was specially asked by Compass to make analysis of pion TMDs, and I made it, and I made all pseudodata and all inputs for Compass, but somehow, after these 5 years, it's completely not used.
I didn't work at the time there, so I'm sorry.
So that's why
but yes, and
I feel myself forgotten. So.
But actually, apart from joking, if you send me the reference, I could bring it up again because we are still concluding the release of this data set. So there is still time to kind of take a look at it.
Sure. I will
it's
send
not finished. As you can see, I was not even using actual data, but pseudo data, because those are not actual release data. So if you could send me the reference, would be really useful.
I will send the reference, and also somewhere inside of your collaboration, all pseudo data and all predictions are stored. I don't know where. And second, could you go back to the comparison of cross sections with TMD predictions? Like this, for example.
Yeah. Oh, wait. Let me go to on the actual.
If I'm not mistaken, the prediction of TMD factorization for pi and rel Yan is quite strongly below the data. Maybe you can correct me.
Yeah.
Something like, actually, at this energy, factor 2.
Yeah.
But you show it's where normalization is exactly perfectly reproduced. So what happens? So either your data kind of 2 times smaller than data of E, which contradicts your previous plots. Either you did something here with theory. So what happened?
In this case, I was using the map, as I was saying, framework, which actually uses some kind of normalization. So this is a model that actually takes into account that.
But I mean, pseudo data cannot just magically increase normalization, right? Pseudo data.
No, they are made
in
on
fact,
the
here you don't see
the
factor 2 of normalization because he put our model and fluctuated the prediction with the experimental uncertainties and nothing else.
So this is basically normalized to the data here.
Yeah, you can see it.
It's already included as a feature in that model. If you use pseudo data, it's already considered.
If you go in the previous slide, the data of Compass are very similar to the data of
E615.
Yeah, okay. And for that data, it was more or less factor 2. Theory prediction was so. Because I think it's one of kind of central, if you wish, puzzle of TMD physics for a moment, that for low energy rel Yan, we're actually really below the data. So we should solve it.
Yeah. This is a known issue of this pi and TMD extraction. So yeah.
It's not only for pi; it's also for.
No. Yeah. I was focusing on this. Okay. Any other question? Oh yeah, Arut.
Do you have the invariant mass of your pairs?
Not right here. No.
Where is it?
Wait, maybe I don't get it. The invariant mass, what do you mean? Is this the high mass Drelian that I was showing? Well, the only mass that I was showing here was this one. Okay. Each in the high mass Drelian, just after the J-psi peak, and you know, getting rid of those high background regions.
One question I always had to Compass people is that if we indeed have a bunch of vector mesons around, and they are like 10 to 6, 10 to 7 more than Drelian cross-section, with a branching ratio 10 to minus 5, it's still a huge number. And the mix of coming from the same rho 0, for example, you can exclude. But if they come from different, how that can be excluded? Is there any check?
Yeah, we have, as I was saying, all this setup is ensuring us a kind of a really clean process at the end of it. So we are excluding all this vector meson contribution.
It was, I remember the procedure was likewise, unlikewise charge, kind of considering them equal and evaluating background through that, but that may not be the same. Anyway, in Monte Carlo you can probably check that.
Yeah, you can just
see whether anything leaks into your into your Drelian, because number of rows is just huge.
Yeah. I mean, this is all done by Monte Carlo simulation, just to take into account also this contribution. It is a known problem, so it was considered. What I can say is like we try to have as clean as possible data in the beginning, and then we exclude all this contribution through the usual data analysis with Monte Carlo procedure and all of this. The issue here, as I was saying, it's also the reason why we limit ourselves to just that high mass region. Yeah. Yeah. Also for Rod 0, all this stuff. That is made after, just as analysis, just to exclude with all the Monte Carlo simulation and try to limit. Obviously, there is always not a perfect, you know, a perfect determination. It's just as good as possible, let's say.
Any more questions?
But it's really good.
Okay, then we leave it here. Thank you very much again to all of the speakers in this session. So there's an hour break now for lunch. The colloquium will start at 1:30 in this room.